This video is all about kinetic energy. We're going to be looking at calculating the amount of energy in the kinetic store of a moving object. Then we're going to look at what difference the velocity makes to the amount of energy in that kinetic store, and we're also going to have a look at what happens when you apply the brakes to an object. So it's got energy in its kinetic store. When it's stopped, it has zero kinetic energy, so where's that energy gone? First thing we'll do is have a look at calculating the kinetic energy, so look at the equation. What we're going to do in words, the kinetic energy is 0.5 or half times the mass times the speed or the velocity squared. So I'm going to put speed squared because that's how it shows up on your equation sheet in the exam specification. That could also be velocity. We'll do this much later on, but velocity is basically the speed in a certain direction. So at the moment we'll just stick with speed squared. In symbols, and I advise you to learn it in symbols, it's far easier to remember it, that's how I always remember these things. We've got the mass times the velocity squared divided by 2. Okay, so mv squared over 2. I think remembering it this way around makes you always remember to have to divide by the 2 afterwards. I would expect you to do the v squared first and then times by the mass and then divide by 2. Okay, common mistakes are forgetting the 2's, so forgetting to square and forgetting to divide by 2. We need to know the units for these, so obviously energy measured in joules, mass measured in kilograms, so if we're given it in grams we've got to convert to kilograms. We're looking at conversions and stuff partway through this lesson. Kilo means 1,000, that's the thing to notice there, so 1,000 grams. And velocity has to be in meters per second. Meters per second. Okay, that's the units. Just remembering this then, kinetic energy basically just depends on 2 factors, the mass and the speed. The more mass, the more speed the object has, the more energy it has in its kinetic store. What we're going to do next is have a look at calculating the kinetic energy in a moving object. That moving object is going to be my son driving his bike along, and what we're going to do, we're going to use these cones spaced out, okay, between 2 sections on the road just outside the house here. He's going to ride along between them. We're going to time how long it takes for him to go from one cone to the other. That'll give us a time, and then we've got this distance, and we'll be able to measure the distance between them. In actual fact, what we're going to do is put these 5 slabs apart. The slabs are all 90 centimeters long, so 5 of those 90 centimeter slabs, that'll be our distance. And if we know the time, we can do speed is equal to distance divided by time to work out the speed. We'll work out the mass, so I'll look up the mass of the bike and the mass of my son, and then we can put that mass times by the velocity squared divided by 2 and work out the amount of kinetic energy that's in him and his bike as he's moving down the road. Let's look at actually using that data to calculate the kinetic energy. As we said before, always start, when it's asking us to calculate something, just start with the equation that we know. To get the kinetic energy, we need to know the mass and the velocity squared. Mass in this case is easy, so I put my son on the scales. He's got his mass. I've googled the mass of the bike, so in total that gives us a mass of 32.1 kilograms. The velocity, what we're going to do is use our speed is distance divided by time. The distance was 5 slabs, 90 centimeters each, so that's 90 centimeters, so divide by 100, 90 divided by 100 gives us 0.9, divided by the time on that stopwatch was 0.75 seconds, so 4.5 meters divided by 0.75 seconds gives us 6 meters per second. So he's travelling all across every single second, going 6 meters. A couple of little things about that. One is, you saw on the slow-mo, the start and stop wasn't exactly on, so there's a human reaction time error there. So there's a bit of uncertainty in that, so it's not going to be exactly that amount. We'd have to do more repeats to try and get that a bit more accurate, a bit close to the true answer. Speed of cyclists walking and running are different things that you need to learn for the paper 2. So we had a quick look at the specification, and I put in cycling into here. You can see actually we have got walking 1.5 meters per second, running 3 meters per second, and you spot the pattern, it's doubling each time. So from running to cycling, 6 meters per second. And you're expected to recall typical values. It doesn't have to be exactly that, because you can go much faster or a bit slower than that, and it's going to depend on the terrain. So we're going slightly downhill there. Now let's use those two numbers to calculate the kinetic energy. EK, mass times velocity squared. I think it's always worth putting out the symbols each time. Mass 32.1 times by 6 squared, divide that by 2, okay, and that will give us 577.8 joules. That's how much energy is in the kinetic store of the cyclist and the bike as they're travelling along. Okay, that's fairly straightforward, just to put those numbers in. The next thing I want you to have a look at is what would happen if we doubled the speed of the cyclist. So instead of going 6 meters per second, we double it and they travel at 12 meters per second. So we get the same equation to calculate that, same mass, but this time it's 12 squared on the end and divided by 2. Now most classes, when I raise this question and I'll say, right, doubling the speed, what's it going to do to the kinetic energy? They think it's going to double it. But we know now, or what we'll have a look at, is the maths and see if that's actually true. So we put that in, we actually this time get 2,311.2 joules. Now it clearly isn't just double 577. In actual fact, if you divide our 2,311 by our 577, you would get 4, which means it's actually 4 times greater. Doubling the velocity has got us to go 4 times the amount of energy in the kinetic store. Now that's because of this v squared. If we went 3 times the speed, you'd actually get 9 times the amount of kinetic energy in that kinetic store. This has some important ideas in terms of vehicle safety. So if you were to halve the speed of a car, say from 40 miles an hour down to 20 miles an hour, you'd actually get 4 times less kinetic energy. So 4 times less energy in the kinetic store to try and dissipate, so you could brake quicker, and if it did collide with something, it would transfer 4 times less energy to that object, doing less damage. The final aspect I want to have a look at today is looking at where does that energy go. So when those brakes are slammed on, we can see the amount of energy in that kinetic store that we're going to have to dissipate to get to 0. We'll have a look at these brakes slamming on in one of what's been the Berry Bullets challenges for this half term actually. They've got to ride along full speed, slam on the brakes and stop with the front fork as close to their water bottle as possible. So we'll have a look at them having a go at that, and then we'll explain the energy changes involved there. Now that energy is going to have to move from the kinetic store of the object to somewhere else to get to 0. So it actually starts to go into the thermal store of the brake blocks, and then that would then dissipate into the thermal store of the surroundings. Next thing that would be useful to go over is just about converting between different units. So we had something here where we had it in centimetres, and we had to convert it into meters. So we had 90 centimeters here. So 90 centimeters we have to do 90 divided by 100, gave us 0.9 meters. Now it's important you can do these conversions. So the key one really is that kilo means 1,000. So if you ran 5k, 5 kilometers, you'd run 5,000 meters. So anytime you need to convert, so 200 grams into kilograms, divide by 1,000 because it's kilograms. Let's keep with that. So kilojoules. So if we had it in kilojoules, that would stand for 1,000 joules. So you got 45,000 joules. Same in here, kilometers, 3.3 kilometers would be 3.3 times 1,000, giving you 3,300 meters. Now the other ones being mega. Mega is a million, so 94 megajoules is 94 million joules. And gigajoules, so giga stands for a billion. So it goes kilo, 1,000, mega, a million, giga being a billion, giga being a billion. So 0.82 gigajoules, for example, would be 0.82 times by a million, gets you 820 million, or in standard form, 8.2 times 10 to the 8 joules. We'll do a separate lesson if you're not confident on doing standard form conversions. We've got our typical other conversions that you need to know. So 12 minutes, how many seconds would that be? So every minute is 60 seconds. So we've got 12 lots of 60 seconds, 720 seconds. Or if we have 3 hours, we're converting that into seconds. You'd have 3 lots of an hour, and each hour being 60 seconds. So 3 times 60 times 60 will get you 10,800 seconds. So you need to be able to convert those, and they will be assessed in the questions at the end of it when we're practicing conversions and doing our calculations for kinetic energy as well. The final idea is calculating the velocity of an object if you know its kinetic energy. Now, it's one of the most mathematically difficult calculations on the entire course, so it's coming quite early in the GCSE course. Let's have a look at how we would go about calculating this. Let's do this in terms of an example. Right, a competitor believes they'll score a strike if they manage to give their bowling ball at least 200 joules in kinetic energy in the kinetic energy store as it leaves their hand. We've got the mass of the ball. Calculate the minimum speed the ball has got to be released with. So what we're doing here, we're calculating the velocity and we know the kinetic energy. So they've given us that there. That's our EK, and our mass here is 5 kilograms. What we're going to do, we're going to write out the kinetic energy equation just as we would always do, mv squared over 2. The great thing about physics here is that if you can just learn these equations, you can then easily access all the other parts of the marks. So let's put in our numbers. We know that we've got 200 joules here, so that's our kinetic energy there. The mass is 5, but we don't know the speed, and that's squared divided by 2. So the only thing we don't know in this equation is v squared. So let's have a look at how we would solve this. Let's get rid of the divide by 2 by timesing by 2. So we'd have 2 lots of 200 on that side. Times by 2 on this side. We've still just got 5v squared. So on this side we've actually now got, I'm going to step by step here. So we've got 400 is 5v squared. We're going to get rid of the times by 5. So we're going to divide by 5. So we're getting 400 divided by 5 gives us v squared. 400 divided by 5 is going to give us 80. That gives us v squared. And hopefully you could then see that to get v, we need to square root 80. So put that in my calculator, 80 and square root, and I get 8.9 meters per second. Now then you have to do a quick check and you have to think, would that be about sensible, leaving the ball that fast? So 8.9 meters per second, it's pretty quick, but that could happen, so it's a realistic answer. So that's the toughest question really they can ask you on the GCSE course in terms of the maths. So it looks like we've done a whole load of maths there. We're just rearranging to find this missing v here in the equation. So you can take it step by step, and then you can guarantee yourself that you can answer any question on kinetic energy. Try these practice questions that are on the workbook, and then we'll be into the next section. Great, so that you understand about kinetic energy now, you can recall the equation, you can apply the equation, you can rearrange that equation to calculate the velocity rather than just calculating the amount of energy in the kinetic store. You understand about the impact of doubling the velocity or tripling the velocity, because it's v squared, that would quadruple it, or go 9 times if you went 3 times the velocity. So now what we're going to have a look at is moving on to elastic potential energy, calculating the energy in the elastic potential store and calculating the energy in the gravitational potential store.